Okay, welcome everyone to this third session of the 2021 Almos conference. This session it appears on the webpage as organized by myself, but actually that's not true. This session was organized by the early stage researchers of one ITN network that is called ProTechTion as the session. ProTechTion is the short name of industrial decision making on complex production technologies supported by simulation-based engineering. So basically, it's a Marie Curie network that gathers several different engineering problems, all with a very strong link with industry. So this ITN has 15 early stage researchers that organize this session. So it will be divided in 3 slots. The first slot is this one, starting right now. The next one will be today at 1:30 after the lunch. And the last one will be tomorrow at 10. So Tuesday at 10 will be the last one of the 3 sessions corresponding to the 3 slots corresponding to this session. So this is a little bit the idea. So we are going to start with the presentations. I encourage everyone to ask questions in their chats, so we have a nice discussion after the videos. So if we can start with the videos now.
Hello everyone, I'm Alessandro Acri and I'm going to introduce to you my project on solid fluid mixture models for particulate volume fractions. The motivation for my project is that in working set while drilling, sanding, grinding and so on, there is a production of much concrete dust in the air, and this dust is a problem for the health and the safety of the workers. Therefore, companies have produced vacuum cleaners in order to reduce the dust in the air and preserving the health and the safety of the workers. And in designing this type of tools, it's important to understand the behavior of the particles in full flow and also some other challenging aspects like the position of the particles, the bouncing on the walls of these tools, and also the particulate volume fraction. In order to tackle this type of particle fluid flow problems, I've considered the safety discrete method decoupling model. This type of model considers the fluid as a continuum and the particles as discrete particles. And it is a suitable model to describe the particle physics better than other approaches like two-fluid method that considers the particles as a continuum. It's true that its computational effort is demanding, but it's less demanding than other approaches that considers the particles as discrete particles. Therefore, it's a sort of compromising method. This type of coupling model is a 4-way coupling, so I'm considering the contact between particles, the influence of the particles on the fluid, and the influence of the fluid on the particles. And this slide shows how these two methods, these two approaches, are coupled step by step using this type of cycles. So I solve for each step the discrete element method based on Newton's law of motion, that gives me information like the position and velocity of particles that I use to determine the particle-fluid interaction force applied to the fluid, that I use to solve the CFD approach based on Navier-Stokes equations, that gives me information on the fluid like the velocity of the fluid, that I use to determine the particle-fluid interaction force applied to each particle, that I use to solve the discrete element method for the next step, and then this cycle repeats step by step. So now I'm going to show you a brief video. In this video you will see how particles behaves, as you can see now, how particles behaves in cubic domain, so enters from the inlet and we can see all the challenging aspects that I've talked to you before, like the deposition of particles, the bouncing on the walls. We can see also how are performed the contact between particles, the influence between particles and fluid. And at a certain point, we can see now how there is an increase of particles inside this qubit domain, resulting in an increase of a particle volume fraction that is also a problem now. We can see this instability where there are particles that are packed to the outlet, and then at the end we can see also the deposition of the particles. So now we can go back to the presentation, and I'm going to present you the conclusions that I reached so far and the outlook for the future. So a safety depth coupling approach to solve problems involving gas-solid mixture model is performed. I've also performed a qualitative assessment, and we can see from that the behavior of the particles is highly influenced by the fluid flow as expected. I've also performed different scenarios that show how the approach can describe the particle physics. I've also improved the code performance, reducing the time simulation. And they've also implemented an high-efficient discontinuous gradient approach to the fluid phase that makes more efficient not only the fluid phase but also the coupling itself, because of the way this approach discretizes the velocity and pressure terms. The outlook for the future are quantitative assessment and comparison with the experiments and other approaches. So before conclusion, I want to thank the European community to have found my project, and thank you very much for your kind attention.
Okay, the next presentation is by Bruno Aguirre. He's doing his study between the Instituto Superior Técnico in Portugal and École Centrale de Nantes in France, in collaboration with Alto Industry. And the name of the presentation is Geometrically Exact Shell Theory with Initial Curvature and 3D Constitutive Models.
Good morning, everyone. My name is Bruno, and I'm here to talk about something that under my PhD thesis, which is the geometrically exact shell theory with initial curvatures and 3D constitutive models. I'm advised by Professor Carlos Thiago and Professor João Correia here in the IST Lisbon, and by Professor Lohan Stanier in École Centrale de Nantes. So Pimenta and Campelo, back in Brazil, in the University of São Paulo, they developed this shell model, which is geometrically exact and it also has thickness variation. And we introduced the possibility of working with initially curved geometries, which was not possible before. So this new feature is implemented by the introduction of a new initial configuration. So basically, using this initial configuration, we're going to create a flat reference configuration where all the calculations are going to be performed because it's easier to work with a flat geometry in this case. We're going to have a mapping in between the reference and the initial configuration of Kirchhoff law of type. So basically, the rotations are completely coupled with the basis. And the total mapping is of a Reissner-Midland type, and of course, it includes thickness variations. The kinematic hypothesis is described by these two equations here. X represents the position of the current configuration, where Z and A plus, respectively, are the midplane position and the position of the director. The parameter S here on the second equation basically controls how the thickness is going to be varying on this problem. So here are some important model details. Of course, it works with large strains and it's geometrically exact. The rotations are parameterized with three parameter Euler-Rodriguez formula, which is it's interesting when compared, for example, with Cartesians, where you have 4 parameters. The thickness variation is controlled by a quadratic equation. So basically, you're going to have a linear and a quadratic term controlled by these two parameters here, P and Q, the degrees of freedom, basically. and they are responsible for these two types of thickness variation. P is responsible for stretching and diminishing of the midplane, of the thickness basically, and Q is responsible for the displacement of the midplane with respect to the thickness. And one of the most important features of this model is that the thickness variation allows the use of full 3D constitutive models. So here are some implementation details. The model is implemented in an in-house Fortran code. The code is in a finite element context using the T63I element. So basically this element is quadratic on displacement and it's linear on rotations and thickness variation parameters, so to avoid shear locking. And it's integrated with MATLib, which is a library developed by Professor Laurent Stanier, which has a variety of constitutive models. So here we're going to see how the model is performing. We have this pinched cylinder example. We're going to use the viscoelastic Ogden-Ogden-Encke constitutive model. You can check this reference for all the details of this the constitutive model. We're going to also be using the same material parameters as in the paper, so it gets easier to do comparisons. This is the disposed in placement evolution. So basically displacement is time dependent, so it evolves linearly until time equal to 3, and then we free the nodes, and of course as a viscoelastic model we should go back not instantly to the original position. This is the geometry here. Of course we're going to have symmetry conditions in this line here and in this line here. We don't need to solve all the problem because it's symmetric. So here is the video. As you can see, until time 3 the problem, the impulse displacement is acting up. When it reaches time equal to 3, it goes back and then it slowly returns to the original position as it should in a viscoelastic model. So in conclusion, we presented a geometrically exact shell model which considers thickness variation and is able to work with initially curved geometries. The model is already implemented and is giving accurate results when compared with the benchmark tests. As a future work, there is a little bit of an issue of membrane locking, which is appearing in some cases, not all of them. Basically, this kind of implementation doesn't have any special device to counter this kind of locking. For example, mixed approximation, reduced integration, or unequal order of approximations. So this would be an interesting future work. I want to thank the European Union for funding this project. These are the references, and thank you very much. I'm ready to take any questions that you have. Thank you.
Good. The next presentation is by Ahmed Aisa Berraires. He's working in collaboration between Pavia University and TU Eindhoven. And the title of the talk is Design Tool for Actuation Control of a Microfluidic Valve Using FSI Partition Approach.
Hello everyone, my name is Ahmed Aisa Berraires and I'm a PhD student in University of Pavia and Eindhoven University of Technology. My presentation is entitled Design Tool for the Actuation Control of a Microfluidic Valve Using Partition Fluid Structure Interaction Approach. Fluid structure interaction is a multiphasic type problem that earned increased attention during the last 2 decades. Several engineering applications rely on FSI simulations to solve different industrial problems in many fields such as aerospace, civil engineering, biomedical application, etc. Such type of interaction requires specific numerical methods to tackle different situations and might be computationally challenging due to the physics of fluid, nature of interaction between the solid and fluids, and structural properties and geometry. In other words, FSI is problem dependent and generally needs fine-tuning with respect to the complexity of the task. The partitioned approach is the most popular approach since it preserves the modularity of the participant solvers and allows independent setups that can be coupled using intermediate coupling solver. This approach performs well when solving two-way fluid structure interaction problems with compressible fluids or low added mass effects. However, it might be unstable for incompressible material coupled with soft, lightweight structures, which requires additional effort to obtain a problem solution. This is the case of our valve under investigation, which is a two-stage pilot valve manufactured by our industrial partner Dolphin Fluidic, which is a company based in Milano in Italy. Simulating the operating condition, namely the opening and closing, is quite challenging because of the different non-linearities present within the system besides the contact and the nearly closed configuration. We would like to solve this specific problem the hard way, assume an incompressible water flow governed by Navier-Stokes equations, which follows the arbitrary Lagrangian Eulerian formulation to allow the deformation of the fluid grid adjacent to the structure. The structure itself, which is made of hyperelastic silicon rubber modeled using the new Hookean hyperelastic material model and discretized using mixed formulation to account for volumetric and shear lock-in. Traditionally, people solve partitioned FSI problems in an iterative manner using Gauss-Seidel fixed point algorithm. This method cannot deal with our specific model due to the high added mass effect and requires under relaxation to stabilize the fluid acceleration. However, choosing the appropriate under relaxation factor depend on the fluid to solid density ratio as well as the model specification. Recently, quasi-Newton method has been developed to tackle this specific kind of problems and has proven to be a robust and an efficient way to couple partitioned FSI problems. It offers an alternative to Gauss-Seidel schemes and is based on the root finding method for black box solvers. This method does not solve the exact Jacobian of the Newton method explicitly because of the limitations of the black box solvers. However, it approximates the inverse of the Jacobian in an iterative manner until time-step convergence. This method offers considerable acceleration to our simulation run compared to the sub-iteration with under relaxation. It can also effectively deal with contact nonlinearities and tends to produce good results in comparison with the well-known exact Newton procedure. Another method employed by some scientists, assuming artificial compressibility within each time-step iteration, has been an alternative to solve our model. In this method, a source term is added to the continuity equation of the incompressible fluid as a function of pressure variation. This pressure variation vanishes once the time-step solution converges. This method can outperform the interface quasi-Newton least square method in some situations. It can also be limited to the adjacent wet interface to become interface artificial compressibility. To conclude, fluid structure interaction simulations have become increasingly popular in engineering applications. However, it's very problem specific and requires fine-tuning to deal with challenging bottlenecks like added mass effect and nearly closed system for incompressible fluids. Stabilization methods has been introduced to deal with these challenges like sub-iteration with under relaxation, interface quasi-Newton method, and artificial compressibility. Additional efforts are still required to deal with different sources of nonlinearities and need a proper understanding of the problem specifications. Finally, I would like to invite you to check out the extended version of this talk in Scipedia for your consideration. Thank you very much for your attention.
Very good. So the next presentation is by Fabiola Cavaliere. She is doing her work in collaboration between UPC, the Technical University of Catalonia, and Swansea University. And her work is in collaboration with the SEAT car company. The title of the talk is Non-Intrusive Proper Generalized Decomposition Method for the Design Optimization of a Car.
Hello everybody, I'm Fabiola Cavaliere and I'm a PhD student. With my project I'm trying to understand how we can efficiently design a new car. The design process is the most time-consuming part of the whole project because it needs a lot of iterations until the best solution is found. This of course represents a waste in terms of time, energy, resources, which is the reason why the industry needs to optimize the design process itself. In my project, I'm focusing on one target specifically, which is the noise and vibration response of the vehicle, a target which depends on the static and dynamic properties of the structure, and it is very sensitive to variations in the design parameters. The problem here is that by adding design parameters to our problem, we increase its dimension, so we define a high-dimensional problem. And when we employ standard numerical methods, we need to test many configurations. Actually, we need to run a computation for every combination of the parameters. And this is too expensive in real industrial applications. Our goal in this project is to develop a method able to efficiently explore all the configurations with only one computation. This is possible thanks to the reduced order methods, which are able to capture the essential feature of a problem in an acceptable amount of time and with limited storage capacity. In this work, we use the proper generalized decomposition method, which presents several advantages. First of all, no previous knowledge of the solution is required, and also it computes a computational vademecum which contains all the possible solutions for every combination of the parameters. Of course, this helps and makes much faster the post-process, which will help in the decision-making of the design. Specifically, I've used a PGD-based encapsulated algebraic toolbox, which was developed in my research group at UPC in Barcelona, which is a set of MATLAB routines able to perform operations between parametric quantities. The main feature of this toolbox is that it can act as a black box, in the sense that the user only needs to prepare the parametric input data, give it back to the encapsulated PGD toolbox, and receive the parametric solution. And by assumption of the PGD method, this solution is defined as a sum of terms, where each term is given by the product of functions depending on the introduced parameters. As a consequence, the post-process is very easy and fast, because the results for a specific choice of the parameters can be obtained in real time by simply performing linear combination of functions. So this result can be uploaded on a tablet, for example, and by simply scrolling on the values of the parameters, we can see in real time how the result will change. So we applied this methodology for the parametric NVH study, which basically consisted in solving a static parametric problem and a dynamic parametric problem. Actually, the dynamic problem in terms of generalized eigenvalue problem, in order to extract the mode shapes and the frequencies associated to the structure. Several challenges were faced during this project because, first of all, for example, we needed to couple the PGD with the inertial lift technique, which is a technique able to solve the static analysis of unconstrained structures. In fact, during the NVH test, the car is assumed to be unconstrained. We developed a parametric eigensolver by coupling the PGD with the inverse power method in order to extract the mode shapes and the natural frequencies. And very importantly, we're able to develop an algebraic approach which allows to consider complex geometric parameters, which is usually a limitation in the PGD method. Everything was made in a non-intrusive format in order to permit an interaction of the method with commercial software, such that the industrial application is possible. Also, we were able to perform multi-objective optimization study, which is fundamental during the design process itself. Let me show you a numerical test where we solved the parametric model analysis of a dummy car. The parameters are the thicknesses of 3 car components, and by means of our tool, we were able to extract the parametric mode shapes and frequencies. And here, in terms of result, you can see how the first 3 frequencies vary inside the parametric domain. Also, in real time, it is possible to obtain specific solutions for precise sets of parameters. And multi-objective optimizations problems can be solved where, for example, we minimize the mass of the parametric car components by maximizing the frequency associated to the torsional mode. You can see the colored points representing the optimal solutions, which are much less than all the possible configurations represented by the empty points. In conclusion, we developed a computational tool which is really able to support designers in the decision-making process. Thanks for your attention.
Very good. We have a couple of questions, but I encourage everyone to add questions to the chat. So the next presentation is by Nick Dave. He's doing his research between TU Eindhoven and ULB in Brussels in collaboration with the OSE company. And the title of the talk is Through Thickness Water Transport and High-Grow Expansion in a Paper Sheet.
Hello. Let's look at how can we model water transport in paper sheets through computational modeling. My name is Nick Dave, and I work with Ron Peerlings, Jerry Mussat, and Mark Kears from Eindhoven University of Technology and ULB Brussels. This research work is part of the MSCA Horizon 2020 European Joint Doctorate Program. The industrial collaborator, Canon Production Printing, is trying to shift towards a sustainable inkjet technology. The industrial printer shown on the right image is used for printing books and magazines. However, using green products means there are moisture-related issues. In this project, we are trying to develop predictive models in relation to the microstructure. Dimensional instabilities are usually caused by inhomogeneous moisture profile along the thickness of a paper sheet, and therefore we need to take into account the dynamic moisture state to reach our objective of developing a one-dimensional continuum model. This model is at the sheet scale. For this, we assume a simple constitutive model. There is elastic deformation represented by the spring in the middle, kinematic hardening shown by the spring dashpot arrangement. The sponge on the left side depicts the moisture-induced deformation or high-grow expansion, where you see that the change in the moisture content, which is denoted by the delta chi, is then there's a product with the high-grow expansion coefficient, which gives us the high-grow expansive strain. Deformation due to inhomogeneous moisture profiles. You could see it in this animation where we start with a dry sheet of paper and we wet it with this moisture profile shown above, and then later it is dried to the initial state. The resulting elastic and inelastic deformation is then studied further with the water transport model, which you see on the left, where the pores, the pore transport and the fiber absorption are considered for the penetration process through the thickness of the paper sheet. We use a certain driving force in this mechanism. We call it capillary suction. This is given simply by inverse relation between the radius of these capillary tubes and the capillary pressure. The resistance to this flow is caused by the permeability, which has a square relation to this radius of these tubes. We also use the concept of saturation here, which gives us the volumetric water content in the porous medium. So using the mass balance or the mass conservation, we write the partial differential equation for the pore transport, which has the permeability, the capillaries, the gradient of the capillary suction, and the pore saturation. We also take into account the nonlinearity in this permeability and the capillary pressure. In terms of saturation, and then we hypothesized the dual porosity medium, wherein we take into account the pore transport and the fiber transport. Using of course suitable boundary condition, where we dry that we wet the dry sheet of paper from the top, and after a certain moisture has been applied, we apply a no flux boundary condition at the top of the paper sheet, and at the bottom of the paper sheet it's always a dry condition, so it's a no flow condition. What we see here are two regimes, namely imbibition and redistribution. You see the imbibition here, which it goes through the speed which is much faster, so it's in the range of milliseconds or 0.1 milliseconds. We also noticed the redistribution regime, which is quite slow, and then this is observed after we change the boundary condition on the top. These timescales help us to understand the fast pore water transport and the subsequent and a very slow fiber absorption regime, which you see on this in this image. So to conclude, we looked at how moisture-related dimensional instabilities could be modeled with computational modeling. Inhomogeneous moisture profile and plastic deformation seem to cause out-of-plane deformations, and the spontaneous imbibition is seen with the time-taking redistribution, which they are related to the pore water transport and fiber absorption. Well, there are certain things we want to look at in the future, to look at an effective constitutive model, and also the effect of drying and hysteresis. So I'd like to thank you for joining, and if you have any questions or comment, please contact me on this email address. Thank you.
Very good. So we have one last presentation by Thomas Di Giusto. He's working on Swansea University in collaboration with the Technical University of Catalonia, and his project is related with the ACI software company. The title of his presentation is Coupling Materials for FSI in Open Foam.
Good morning or good afternoon, everybody. My name is Thomas Di Giusto, and I'm a PhD student at the Zinkevich Computational Engineering at Swansea University. My project is entitled A Novel Arbitrary Lagrangian Eulerian Formulation for a System of First-Order Conservation Laws in Fast Solid Dynamics. In this short presentation, I'll state the area of applications we are interested in. Then I will present our ALE framework for fast solid dynamics. I will show some numerical results, and I will conclude on the perspectives we are currently investigating. So fast solid dynamics are about large deformations induced by high energy impact, usually in little time. There are numerous situations corresponding to fast solid dynamics in the industry. Crash tests in the automotive industries, for instance, defense, biomechanics, many more fields. The difficulties of these simulations lie in the presence of large deformations, a poor distortion or entanglement of the mesh, the requirement for complex constitutive equations such as memory-dependent models, or non-smooth response of quantities such as the pressure. The prevailing approach is total or updated Lagrangian, but applying the Eulerian approach would let us borrow techniques from CFD. Also, in the past years, the ALE technique, where the mesh and the quantity move in a complementary fashion, has gained in popularity in computational structural dynamics. Let's now move into the core of our framework and see its main features. We are using an ALE approach based on the composition of the natural deformation gradient. The material and spatial deformation gradients are solved instead of integrating the displacements. The integrations are now performed on the referential domain. The framework is based on a set of first-order conservation laws. As you can see on this slide, the equations are hyperbolic and have associated jump conditions which enable us to use an acoustic Riemann solver for stabilization. The mesh is distorted via conservation law and user different parameters. The material velocity is solved and its stress tensor is based on constitutive parameters to control the level of deformation. Note that this law is also hyperbolic. The wave speeds have to be rescaled using this formula because the integration is now performed on the referential domain. The spatial discretization is based on the vertex-centered final volume method and is implemented on OpenFOAM. The time integration is explicit, and the computation of the time step depends on the spatial stretch. Let's now review some numerical results. First of all, this translation problem highlights the role of the geometric conservation condition in an ALE context. As we can see on this graph, a satisfying computation of the pressure is achieved when we solve for the material deformation tensor F and Jacobian J. A similar conclusion is drawn upon the velocity and the displacement. In this swinging cube problem, a convergence analysis is done based on the following closed-form solution for small deformations. If the material motion is prescribed to the same magnitude as for the spatial motion, a second-order convergence is achieved for the velocity components as well as for the stress, where the results are very similar to a total Lagrangian simulation. When the motion is solved, whether to a small or a high intensity, the second-order convergence is maintained for the velocity and for the stress. In this last example, a column is bent by a linear velocity profile. A prescribed material motion of high intensity is prescribed along the xy plane, and the robustness of the code is studied. As we can see, the displacement along the x-axis converge in the same manner in ALE and in total Lagrangian. The same observations are made for the y-axis. Besides, the preservation of the energy is remarkably good in total Lagrangian and in ALE as well, for a fine mesh. Now, as for the current and future objectives, we implemented more advanced constitutive models such as plasticity, as you can see in the middle picture. We are working on thermoelasticity. We are working on alternative mesh motions to save up as much spatial stretch as we can. And we started applying the framework to FSI problems, such as the one where coupled emerged specimen that you can see on the right. Thanks, everyone.
Okay, that concludes all the presentation for this first part of the session. So let's move to a little bit of discussion. We have a couple of questions. If someone else wants to add a question of on any of these talks, please go ahead on the chat. So we have a couple of questions for Bruno. The first one is, in the results presented, you show a 3D geometry. It is only a visualization feature, or you have something else that, for example, that's
could you hear me?
Yeah, we hear you well.
Okay.
Something like shell to solid coupling capability.
So hello. So trying to just answer this question, it's actually a post-processing thing that we developed. Basically, we create solid elements and we export the results on the solid to these elements. It's interesting because usually when you see shell theory works, they never show what's happening on the thickness direction. And well, with this we can show, and it's also because we use these quadratic solid elements, we can capture the deformation of the thickness.
Okay, thank you, Bruno. Second question also from Paulo is, could you elaborate a bit more on what based your choice on Rodriguez parameters to describe rotations? How do you treat singularities?
Yes, when you say singularities, I'm supposing that you mean when you reach very high rotations, it's actually the solution is singular. Well, basically the Euler-Rodriguez is interesting because it has only 3 parameters. When compared to quaternions that have 4, so it's 1 degree of freedom less on the nodes, on the rotation nodes. The singularity is not really an issue because it only happens with like very, very high rotations. But in the case that you want to use the same formulation, you can use an updated approach. So basically, we're gonna store the rotations at each iteration or each pseudo time step, and then you can apply as the initial one in the next iteration. So this problem never appears, basically. Of course, this comes with like a drawback. Basically, the problem becomes path dependent. And also, you're going to have to store, it's a memory problem because you're going to have to store the rotations at each integration point, at each element. So it's actually a lot because it's a 9 degrees of freedom more, not degrees of freedom, 9 parameters more that you have to store. So yeah, that's it.
Thanks, Bruno, for the answers, and thanks, Paulo, for the question, for interesting questions. I have some fast questions for Bruno also. When you say exact geometry, how are you describing the geometry? Yes.
So the geometry is described by the model is geometrically exact, but so this is the model, no finite elements. When you come to the finite element, the geometry is discretized using this quadratic element. So for example, if the representation is not exact, basically.
No, you're talking about the visualization.
No, I'm talking about when it comes to the finite element mesh.
Okay.
Then you use a quadratic interpolation, which is the order of the element, basically.
Okay. And this, do you have an idea of if this quadratic interpolation, I think that you're using on the thickness, if this is enough to keep the geometry exact, or how accurate is this quadratic interpolation that you are doing on the thickness?
Yes, well, it's an hypothesis because we're working in this shell framework, so we're never going to be able to capture very, very complex stuff in the direction of the thickness. But for the benchmark tests that we've been carried on right now, the solution is basically the ones that have exact solution, the solutions they're exact. The thing is that they don't evolve too much on the thickness direction and the complicatedness of this thickness direction. So it's a bit hard to comprehend and to see, but for now it's working very nicely. We don't see any problem with that.
Very good. Thank you, Bruno. So I'm going to move to the next question to Fabiola. Yanis asks, in slide 6 or 7, you introduced 2 functions, f and g, that map randomness of the input to the randomness of the output. Could you give a brief explanation of how these functions are calculated?
Okay, so hello, everybody. Thanks for the question. Thanks for asking. I guess it wasn't clear because actually what I was trying to show on this slide, it's not randomness of the inputs. Actually, this is not the case. I was showing parametric dependency. Anyway, if the inputs are random, I guess that we have an explicit dependency of the functions, so we could compute the probability distribution of the output. But actually, as I said, what I was trying to show is the parametric dependency. Maybe I can share the screen a second to better explain that. So this is the slide you were referring to. And this is at the base of the proper generalized decomposition method. Maybe I can simply show a fast, let's see where I have a back slide. The idea here is that we have an output which depends on parameters, a set of parameters mu. And so what I'm trying to describe is the dependency on these specific parameters. Imagine, for example, in my application, I'm considering a car structure. So for example, the parameter might be the thickness of a car component. And this is something that the user, the designer knows. So he knows exactly what is the input, what is the parameter. He will vary this specific parameter in a certain range. So it's not random in this case. And the idea behind the PGD is that this quantity can be represented in a separated format, which means that it is given by a sum of terms where each term depends on the parameters in a separated way also with an affine decomposition. So where each function, so we have spatial terms describing the physical space, and then we have parametric functions that describe the dependency on the parameter, right? And how do we compute that, if this is the question now? We have a solver scheme, which is typical of the PGD method, which is based on, first of all, computing each of this term one by one. So some kind of enrichment of the solution. And for each term, we need to employ an iterative scheme, because this is actually, you want to find this expression, which is a nonlinear problem now. So we need to assume an iterative scheme, which in this case, the simplest one we can use is the alternating direction scheme, which basically consists in solving, in first assuming that one function is known and solving the problem, or better, to assume all the functions known and assuming that only one is unknown and solving for this one, and that some kind of a rotation, we assume that all are knowns except one, and we iterate in this sense until we reach convergence. So this is, let's say, the scheme, the solver scheme behind the method. I don't know if I've answered the question.
Thanks, Fabi, for your answer.
Thank you.
Okay, I'm going to move in the order of the questions. So the next question is for Nick Dave from Christina. The question is, I didn't understand how to take into account or measure pore distribution. Is it a state variable or it is related to displacement in a microscale?
All right. Yeah. Hi. Hello, everyone. You can hear me well, Sergio?
Yes. Yes, we hear you very well.
All right. So redistribution, it's actually based on the state variable saturation, which is the normalized water content at a certain material point. And the hypothesis we have for the state variable is that we consider this bundle of tube model along the thickness, right? So parallel tubes along the thickness. And we assume that the smaller pores, so the smaller tubes are filled first, and then eventually the bigger ones. However, these smaller tubes have a lot of friction. So the permeability of the bigger pores is much higher. So it's mostly like a zigzag pathway. So the smaller tubes keep filling up at a material point, and the transport happens from the bigger ones. The bigger ones will transport to the smaller tubes, which are at the next material point. And then eventually this process will continue. With imbibition, what happens is, because all the pores are completely filled, so there is a lot of, the permeability is high, so the bigger pores are constantly, because there is infinite amount of water, they're constantly transporting water. In redistribution, there is sort of a locking mechanism, to say, because the water is kind of restricted in these small pores. So that's how we define redistribution, where the transport sort of shuts off, because these smaller ones, the small tubes can't transport much more water, and the bigger pores are empty in that case. So that water just stays there and doesn't move. But it moves, but at a very slow rate is what we have seen. And the idea here was to validate the experiments. Canon or OSE, the former name. They have performed certain experiments where they see this sort of mechanism, not, of course, at this pore level, but at the sheet level, they see that only half of the thickness of this sheet is completely is wet, and yeah, that takes into account that helps us to define this redistribution. It's not, of course, a state variable, and I think there was another question about the deformation. So it's a loosely coupled model right now. We're not taking into account any swelling of the pores, so the pores don't change sizes right now as they get wet. But we couple it one way. We first look at only the water transport and then couple it and look at one-way coupling and looking at the mechanical deformation. But that I didn't present in this video. Probably next time.
Thanks, Nick. So if I understand it well, just for continuing with in the same direction as Christina question,
yeah,
you have a hydromechanical model, but you are coupling some 1D model that basically is acting as a constitutive equation. And then you have, I don't know, if a 3D model for the mechanical part or the hydromechanical part. Is that correct? I'm not sure how is the connection between the 1D model on the tubes and the 3D model of the paper sheet.
No, there's no 3D model of the paper sheet. Sorry, we are
Okay.
also looking at 1D or just 2D for the mechanical model as well, because we are interested in only the sort of expansion, so the strain or the curvature of these sheets, and that we can easily get from the 1D or 2D model. We're not going into 3D right now.
Good. So and you're taking into account that these tubes are all a long thickness, right?
Yes.
These are the big tubes or the. I mean, it is realistic for a sheet of paper to assume that these tubes are across the thickness.
Yes, that's a good question. So there are varied models to. So it's a porous medium, but it is a fibrous medium. There is a lot of literature on, for example, flow in rocks and soils, where they use sort of beads in the porous medium. Right. There was one talk in the day as well at Atmos today, where they're taking into account beads as the porous medium. But for a fibrous medium, I guess it's a valid assumption to assume, because the porosity of the medium is around 50%, and with a high permeability. So parallel tubes, I guess, is sort of a reasonable assumption for this, instead of beads or any other fillers, to say. What we are actually interested in is looking at the time scale, as in. So we see, or actually Canon has observed in their experiments, that there are multiple timescales which are involved in this mechanism. Not only pore transport and fiber transport, but even the swelling happens at a different timescale. So identifying those timescale is probably one of the main outcome of this research, where we are able to identify the pore transport, the absorption to the fibers, and then how the fibers swell and the final deformation we see at the sheet level.
Okay, thank you very much, Nick.
Yeah.
Nice work. So I have some questions for just a first question for Alessandro. Alessandro presented the simulation of the particles in the fluid. with this discrete element method coupled with a flow model. So I understand that computing the contact between all the particles it's quite expensive computationally. Usually this is something that it takes quite a lot of time in 3D. So my question is, why do you need it? What is what you are trying to model that you need to simulate particle by particle?
Well, hello everyone. I don't know if you are able to hear me.
Yeah, we hear you well.
Okay. So thanks for your question. So the fact is that as I've tried to explain with my 5 minutes presentation, I'm sought also to taking in account as much as possible precise particle physics. So I'm trying to understand better the behavior of particles with this such of difficult and challenging aspects, mainly the high particle volume fraction inside this fluid flow, and having a preciser model is better to achieve this type of achievement. So I don't know if it answered your question.
Yeah. Thank you. Just another very fast question. Do you have some measured data from Hilti to validate your model?
Well, I'm trying to let's say make a sort of improvement in this type of field, but I haven't yet a measurement from Hilti. So yeah.
Okay. Thank you, Alessandro.
You're welcome.
So there is 5 minutes left. I would like just to do a very general questions. One question for all the speakers in this session, which is not a technical question, but I find it personally quite interesting. Do you think that the development that you are doing will be used in practice in the company that you are working with? I don't know, in the order of the presentation, if you want, Alessandro.
Well, I hope so. Well, actually, this type of problem can also be used for other types of situations theoretically, but I have most developed it considering the problem that Hilti has. So yes, I hope that it can be used for many situations and also by Hilti, but it depends on how much they are, let's say, still interested in this type of solution. So yes, as far as I know, they are interested in it, but maybe the situation slowed it a little bit more than expected the collaboration. So yeah.
Okay. Thanks.
You're welcome.
Bruno, you are working with Alto. Okay, I'm not sure if
Sorry,
we have...
can you repeat the question?
Yes.
I didn't hear.
If you think that your developments will be used by Alto.
I do hope so. Well, it's interesting because they have this issue. Well, it's not exactly what I developed here in the presentation, because this is just part of the PhD. But the final objective, yes, because they are having lots of difficulties to the regular engineer for him to implement this kind of materials because of the fire issues. Now, if they do, we can create the safety guidelines that would help for the regular engineer to actually apply this material in construction, which is the final
final objective. So yes, I do hope so. They're going to use it. Yes.
Thanks, Bruno. Ahmed?
Hello? Can you hear me?
Yeah, we hear you well.
Yeah, okay. My PhD started from a problematic that the company advised us to look for. And it's that the FSI problem that they are working on did not converge, and they have issues to make this simulation work. So my tasks, I started by trying to understand what are the issues that they have been going through. And I figured out that they cannot solve the problem using the traditional methods. And this is due to the fact that we have this kind of incompressible fluid that is coupled with a very soft, lightweight structure. And this will create an added mass effect that will just make the solution fail. So the simulation will crash and they could not solve it. So what I've been doing is that I try to understand how can we stabilize the solution and what are the numerical methods that we can use. And after that, I will explain them why their simulation, why their works did not succeed. And after that, I will explain them what are the numerical methods that they need to use in order to solve this simulation in the future in an optimal manner.
Okay, thank you, Ahmed. Fabi?
Yes, so
very fast because we are having 1 minute left. Sorry.
I think we can apply it for real. Actually, we are working on that, and there are good chances. Of course, now we are trying with simple models, but up to now it works.
Very good. Thanks, Fabi.
Thank you.
Nick?
Yeah, I think in my case, the company Canon is quite interested in this problem. They want to understand because in the future they want to use only water and uncoated paper, and which is a very susceptible combination. They just deform right after wetting. So they want to try this. They want to understand more of this deformation mechanism. So I think it should be useful for them, and they look quite interested in this research, of course.
Thanks, Nick. And Thomas?
Yeah, I'm going to be very concise. So yeah, short answer. Yeah, I think the company I'm working with is quite interested because well, they are developing softwares in this scope. They are always trying to find a new manner to solve time of computation. And well, because what I'm doing is has not been done with tetrahedrals, has not been done on the framework of the company. I think that they are really interested, I think. Yeah.
Okay. Thank you very much, Thomas. Okay. Thanks to all the speakers and also the audience. Let me see if I can share my screen for a moment. So this session ends here, and we are going to continue after lunch at 1:30 with the second part of the protection session. So thank you very much all, and I hope to see you back at 1:30.